Lecture 2, Tangible Interaction. Here's the overview of what I will be talking about today, starting with the traditional interface and talking a little bit about what the sort of thinking model is behind those computer interfaces, and then moving on to the idea of external representation, which I will explain. And from the idea of the external representation, we can start to think about what it means to design tangible interaction. I'm going to give you a lot of examples of tangible interaction, some videos as well. So I hope it's going to be a fun lecture. And next lecture is going to dive deeper into the theory behind it, as I already hinted at in the lecture at the end of lecture 1. External representation is only one aspect of embodied interaction. And we also want to talk about the social situatedness and the skilled sensory motor aspect of embodied interaction as well. So that's going to come in the other lectures. But let's start here with what we are familiar with historically. The interaction with computers, of course, used to look like this. When I was young, this was what a computer looked like. You had to type in commands at the prompt, and then following the command, the computer would give you back some information also in text on the screen. There was no memory of that. You could never go back to earlier things. You had to type in new commands to invoke certain information like what is in the directory. So there was a lot of people constantly typing dir, which was the DOS command for dir was the DOS command for directory, to know what files are in what directory you're in and what files are in it. And you had to constantly do that again because of course you've forgotten from the last time and it was already floating from your screen. And then of course a big innovation at some point was the idea of Windows. Windows icon mouse pointer. The idea that using a mouse device you could simply click on a picture that would represent certain kinds of information or commands or applications. And the whole metaphor was, of course, called the desktop metaphor. It was the idea that you would be in an office and you would have a file cabinet with folders in it. Folders were physical things, paper things that you put your documents in. And right now we still are using those metaphors readily. And we have almost forgotten that they were actually physical things in physical offices in the 1950s and 60s and so on. Now, in all these interfaces, it is still the case that we think mainly about information as having to be represented somehow. So the main objective of designers of these kinds of interfaces between a human and a computer are thinking about the right sort of representation of information in such a way that there can be an efficient transfer between the user and the computer of such information. So the basic sort of theoretical conceptual model behind this it is that a human user is separated, as we saw in lecture 1, separated into, on the one hand, a mind, which contains all the information that a person has and is thinking about, and on the other hand, the physical body through which this mind is interacting with the computer. And for the computer, it's the same thing. The computer also has a physical body, physical machine with this mouse and this graphical screen with pictures on it. And that is connected internally to the digital data stored inside of the computer, right? So there's a symmetry here. The both work on the same sort of conceptual idea. And in a way we can say a human being is like a computer. That's exactly what cognitive scientists at the time that also these human-computer interfaces were starting to become more commonplace was exactly what cognitive science was saying, right? So first, both computers and brains are assumed to sample information from the world. So you look into the world and you get data from the world. We call this perception. Information goes in to our system. Then inside our minds, and for the computer the same, inside of the software of the computer, the, the data about the outside world is represented internally, right? We call this a mental model or a representational model or internal model of the outside world. And we think about that the same way for computers as we do for human beings, right? And that's interesting to look later about what the interaction between the two would then mean, right? It's quite convenient, of course, to think about the user as essentially the same kind of thing, the same kind of system as the computer. Um, Now, then the next step is that once you have this internal model of the outside world, so suppose I have some kind of model of the city in which I live, like where everything is located. I have a sort of map in my mind of the outside world. Then if I want to go somewhere, I can internally make a plan for how to navigate based on that map, right? So I can reason about the world using the internal model. And that is something that we call computation. So if we start to move around stuff in our internal model, comparing stuff, putting things in order, exchanging, combining, and so on, then we're actually doing computing. Now, once we're doing that, we can compute the right appropriate action given any situation that we're in. Now, that's literally what computers do. I mean, that's how we build them. So this is just the definition of computers. But it's also, for traditional cognitive science, the assumption of what brains do. So the idea is that brains basically do the same kind of thing that computers do. Now, if you now think about the interaction between a human and computer, then the exchange between a human being and a computer would be, let's say, information that is in my internal software system needs to get into the computer's internal software system, or information that's in the computer's internal software system needs to get into my internal software system, my mind. And so we need an interface. We need some way of getting the data out of my brain into the computer's brain and vice versa. And that we call the interaction, the human-computer interaction. And one part of that interface is our own body, our hands, our eyes. We cannot readily change that at the moment. I mean, so we're getting there, but that was traditionally just a given. On the other hand, at the side of the machine, of course, we can design everything we like, right? So we can design linguistic command prompt based interfaces, and we can design graphical desktop metaphor interfaces or what have you. And that's, of course, what human computer interaction has been all about. Now, there was one very influential psychologist who went into design and started talking with big companies like Apple and so on. And this is Don Norman, is sort of a big guru of human-centered design in human-computer interaction. Very famous guy. So if you have never heard of him, please look him up. He has a nice website also, which I didn't register here, but which I will put in the video. And the idea of Don Norman is that, so the idea of Don Norman is that we actually can use the outside world as part of the mental representation that we need to understand and solve problems. Donald Norman calls this knowledge in the world. He says we human beings make use of knowledge in the world. We don't only use knowledge that's stored inside our brains, we also use knowledge that is out there reliably right in front of our eyes, so we can touch it, grab it, manipulate it, and so on with our hands. And one way to use this in design would be to create natural mapping. So the picture here, if you see it, I don't know if you recognize what it is, but it is a kitchen stove. And the idea of the kitchen stove in this way would be that you can immediately see which button belongs to which stove. And if you align them on one row, that's actually very difficult to keep in memory which button belongs to which stove. But in this way, it actually becomes trivial, right? You just see the pattern and you match one-on-one the pattern of the buttons, to the output. So for example, these are all wrong natural mappings. So the natural mapping that you would expect to be there is actually not mapped. The mapping that you would expect there to be does actually not map onto the function. So for instance, this top one here, um, you have to, this is not a button, right? So you have to turn it, but it looks like something you can press, but you can't. The second one is even worse. This also looks like a button you have to press, but in fact, I don't know if anybody knows, but what you have to do is you have to put your hands under it to activate a sensor. Or this one here on the right side is also very interesting. Um, you would expect that you have to rotate it to get the water, but that is actually to make it hot, and then nothing comes out, and then you have to actually pull it out in order to get the water. But if you are a child, you have tried it already and you first made it hot and then you pull it out and you get hot water. So it is also a very dangerous one. This one is also nice. I will show it. You would expect it that you can turn it, but no water comes out. So you think it's broken. And then, in fact, maybe by accident, you find out that, whoa, I break. Oh no, this is actually the function. It's actually how I should do it. Right? So you think you break something and that is the actual function. A nice example also of a terrible natural mapping I once found in Eindhoven. They've since then changed these machines, but this is for getting a parking ticket. And what you see is that the buttons to activate the parking ticket, they look like the buttons that are described in the explanation above in the guide, but they are very confusing, right? Look very carefully. You have to press the green button at some point, but the green button is somehow not there in the way you would expect it. And then there is a red button, but that looks like the cancel button, annuleren. And then what is shaped like the cancel button is actually a green button. Well, you see it. It's a terrible natural map. So this is a good example of how to do it the wrong way. And it shows you that if you would put information out in the world in the right way, it would make it very much more easier for our brains to handle it. We wouldn't have to think so hard. So what Scott Klemmer talks about when he talks about embodied interaction, he says we think not before we start doing something. We think along with and through doing something. So by physically manipulating things and objects and interacting socially with other people, that's the process through which we do our thinking, right? So this is very different from Descartes, who thought that thinking was something you did while sitting in your comfortable philosopher's chair and shutting down, literally shutting down the whole world away from you in order that you would finally have time and space and the rest to think, right? But this is the kind of thinking that Scott Klemmer is talking about. Is the kind of thinking that you do in action, right? You're busy with trying to fix something, and as you're trying it out, and how does this button work? How do I screw this thing onto it? Oh, this is how it works, right? So it's thinking through doing, learning by doing. That's the usual, normal way in which people think. And there's a lot of aspects to it. It's much about learning, so it's always a sort of a process and gradually getting the hang of something. Gesture is very important in it. There's something called epistemic action that we will return to later, so I will skip it for now. We prototype things, so we sort of already make it a little, and as a sketch, we do sketchy kind of movements and actions, and then we find out, oh, that works, and then we go on with them. Designers, of course, know this very well. And we represent out in the world, and this helps us solve problems by representing the problem in a different way. And Herbert Simon, who was a famous cognitive scientist, early cognitive science, already said this. So he was part of the traditional cognitive science um, guys, so to speak, but nevertheless, he was very keen on this. He said, solving a problem means representing the problem, so to make the solution transparent. So you're not literally solving the problem, you're just presenting it in a different way, and then suddenly you see, it's very easy. And you can think about the kitchen stoves of Donald Norman in this way. If you put the kitchen stove buttons in a line, it's sort of a difficult memory problem, like which button was which one. And then if somebody arranges them in the right in a square for you in the right way, then suddenly the solution becomes transparent. You immediately see which button goes with which stove. So that's basically the idea of it. That's the theory. Now the examples. Tangible interaction. So I'm going to show you a couple of examples and the people that designed them to show you. And it's all about the same idea that you want to get information that people need in order to do a task or solve a problem, and to put that information right in front of their hands and their eyes so they can manipulate it. It's always there, and they don't have to use the computing power of their brains to solve that problem. The oldest example of tangible interaction is maybe Durrell Bishop's marble answering machine. So this is part of the legacy of tangible interaction. So we definitely need to see this.
1 p.m.
Hi Simon, it's about 1 o'clock now. I was wondering whether you're going to come to the football. It's the weather's a bit wet and rainy, so I understand if you don't. Other than that, well, yeah, give us a ring if you're in. Okay, bye.
.45 p.m.
Hi Emma, it's Val.
3:30 p.m.
Hello, a message for Simon Phipps. Your flight is BA 6213 at 12:30, Monday the 15th of October. Your job number is BS 436215 and the pickup address is 44 Camden Mansions, Kensington Mall. Bye-bye.
.45 p.m.
Hello Simon, it's George. Could you give us a ring? My tone number is... Talk to you later. See you. Bye.
So what you saw in this movie, like in the old days, an answering machine was very cumbersome because you had to go through a menu that was structured in a certain way, and you had to use the buttons of your phone to, for example, select the third message and delete it, or listen to it, or go back to the first message again. Oh, I deleted that already, so I can't go back to it, and so on. So there was always very inconvenient. In this way, you have this funny you get a lot of things sort of for free. So for example, if the marbles, each marble represents a message, if they are in a certain order in the tray, you can just pick out the fourth one and rearrange it. You take it out and you put it somewhere else. It's very easy to do, right? It's almost trivial to do it. Whereas doing that with a button interface by selecting 3, going to menu step 5, and then going back up the tree and so on, and remembering what was the code for going back or forward and so on. It was terrible. So you can see by representing the problem in this way, suddenly things become very easy. And the reason that they become easy is that suddenly you can use all these old skills that we have for manipulating physical objects, putting them side by side in a row, changing them in the order and so on. We do that all the time since we're kids, right? So we already know how to do that. And then the problem of answering a call becomes very easy. This is Fitzmaurice. He was one of the first people who wrote this paper called Graspable User Interfaces from the GP lab in Toronto. Very famous. So we're going to look at the movies, and you see it's just more of these examples of how manipulating physical objects that represent digital information makes the task easier.
this part of the panel, we can take off a container element and move it to another destination. As soon as we move it to this destination, it will immediately be registered by the system, and you can see the movement indicated here on this element, which is an alphanumeric display element. If we now would like to have more information displayed in this element about this container, I can show you how this board enables you to move around the functionality of your computer system. I have here a special element. It is called a show element. If I put this show element next to a container element and push the button, then immediately after I will have the information about the container element monitored up here and shown in the display. Of course, I have more than one line of information connected to this element, and here I have convenient push buttons so I can scroll the text and see the various kinds of information I have.
This is the space multiplex condition where we're using specialized devices. And here you see the ruler device. Here is the stretchable square. This is the flip brick. And this is the rotor. And all the targets will start moving around randomly on the screen. And the job is for me to match the targets as best as I can using the devices. And you notice that every once in a while, one of the targets will dart off, and I need to service that right away in order to get the best score. This is a space multiplex condition where we're using the generic devices where we have a puck and a brick for each of the widgets. So in this we have the ruler widget being controlled. Here we have the stretchable square being controlled. This is the flip brick being controlled, and this is the rotor being controlled. Do you notice that there's graphic overlays for each of the tablets to let you know which pairing controls which widget? And so same as before, I'm trying to use the devices to match the targets as best as I can. This is the time multiplexing condition where we're using a puck and one brick to control all four of the virtual widgets. And the puck is represented using the arrow cursor on the screen, and the brick is represented with the cross cursor on the screen. And in order to select each of the widgets, we have to first select one of the handles on the widget and use the puck button to attach to it. And the brick is automatically attached to the widget, and then we can manipulate the widget and then release the button to detach the widget. And so now I can go around and try to match the targets as best as I can.
John Underkoffler was the guy that I already mentioned. He was the guy that helped design the movie Minority Report. He has this framework which is very handy called reality-based interaction, and he says there's 4 different things that the real world offers you, sort of gives you for free, and if you use those aspects as designers, you make the task much easier for users. So one is to use, for example, the idea of naive physics. So if things fall down, they will fall down until they hit something solid, and then they stay there. So that's kind of the stuff we take for granted. You don't have to explain that to people. And if you do it in a way that doesn't live up to the rules of naive physics, you make the task difficult because you get surprised. People think, hey, why is it suddenly this object is going right through the other object? That's not possible, right? Same thing about everything to do with our own bodies. So we we know a lot. We have a lot intuitive knowledge about our own bodies and what's up and down, for example, and what's in front of us and behind us. So if you can make use of that, that's going to make life very easy for users. We have an environment awareness together with our skills. So we know, for example, how far away something is. Is it so far away that we can grab it, or can we just not grab it with our arms? Oh, but if we have a stick, we can suddenly reach out to it. We have an intuitive feel like, oh, then I could hit it, right? So if you put stuff physically around people in a way that makes use of the space, that makes stuff easier. And then finally he talks about social awareness and how we interact with other people, but we're gonna skip that because we're gonna return to um, the that in a later lecture. Give you one example of his. What's interesting in this example, for example, this is an education example to learn to deal with the laser. So if you want to train yourself learning about refraction of light with mirrors, you can use these simple blocks to play around with the way the light is reflecting in the mirror. So these little blocks are mirrors, and on the left you see the laser source, so to speak. But it's all, of course, fake. It's all a model with digital information projected on the table. But because you also can see the corner angles, the numbers, the mathematics that go with it, you can sort of by playing around, you can get a feel for the mathematics. This I like this example especially because very often students will have problems sort of intuitively feeling what orders of magnitude are and whether something gets bigger or smaller and when you multiply it twice or when you change the angle in this way, what happens to all these numbers, right? And if you combine mirrors, it becomes even more difficult. But if you can you do it in this way, you can play around with it just like you would play around with toys and find out how when things so it's sort of this naive physics kind of approach. You play around with it and at the same time, you can constantly check the theory against the numbers that are on the table. And I'm very sure that if you do this for a while, you will learn to feel lasers in the same way you learn to play a guitar or whatever, which is a very different approach than the more top-down theoretical textbook kind of approaches that are most common with these kinds of topics.